Welcome to The Explainer. We're diving into something pretty wild today, a huge hidden crisis in physics, of all places. Yeah, our most successful science. For about 100 years now, it's been slowly unraveling, and it's making us question everything we thought we knew about reality.
Okay, let's just pause on that for a second. That is a huge claim. What David Albert is saying here is that our big project, to figure out what the world is really like, it basically hit a brick wall a century ago, a philosophical brick wall. And honestly, we're still trying to figure out what to do about it.
All right, so here's how we're going to break this down. First, we'll get into this identity crisis that's shaking up physics. Then, we'll look at the big puzzles, the stuff that literally keeps physicists awake at night. We're talking about the measurement problem, the mystery of time, all the good stuff. And then, we'll see where the search for answers is leading. And spoiler, it's taking us to some very strange places, including, back to philosophy.
So what is this crisis really? Well, at its core, it's kind of like a family feud, a really, really big one. We have these two incredible theories, the absolute pillars of modern physics, and they just can't stand each other. They fundamentally contradict one another.
So on one side, you've got Einstein's general relativity. It's beautiful, elegant. It describes the big stuff, planets, stars, galaxies, gravity, with these smooth, continuous curves. Then on the other side, you've got quantum mechanics. This is the theory for the super, super small stuff, atoms, particles. And it's weird. It's all about probabilities and graininess. Now, here's the kicker. Both of them are unbelievably accurate in their own realms, like crazy accurate. But their basic stories about what reality is, they're totally at odds. It really is like having two perfect manuals for the same machine, but they're written in languages that say completely opposite things.
And this right here, this shows you just how deep the problem goes. See, physics used to be all about painting a true picture of the world. What is reality was the question. But then quantum mechanics came along, and guys like Niels Bohr basically said, nope, that's a dead end. And physics, well, it kind of gave up on that dream. It retreated. Instead of asking what the world is, it started just asking, okay, what numbers will our detectors show? The question of what's happening when we're not looking, that got labeled unscientific, which is a pretty big deal.
Okay, so that brings us to the first major puzzle, and this one is a real mind-bender. It's the famous, or maybe infamous, measurement problem. This thing gets right to the core of just how strange quantum mechanics really is. So here's the part that just completely shatters our common sense. According to the math of quantum mechanics, the famous Schrödinger equation, before you actually look at a particle, it doesn't have a definite location. It's not here or there. It's everywhere it could be, all at once. It's this blurry, ghostly cloud of possibilities. Think about Schrödinger's cat. The math says the cat is literally both alive and dead until you open that box.
And that leads to the billion-dollar question, right? If the deepest law of physics we have describes this world of many possibilities, this wave of potential outcomes, then why, when we actually look, do we only ever see one thing? Why does reality suddenly snap into focus and pick a single result? We see a live cat or a dead cat. We never ever see the alive and dead cat that the math seems to be telling us is there.
Well, physicists have thrown a few ideas at the wall to try and solve this, and honestly, they are all completely wild. I mean, just look at these. Some theories say, hey, maybe the equation is just a little bit wrong, and this wave of possibilities just collapses all by itself. Others, the hidden variables camp, say no, the particle always had a real position, we just didn't know it. And then you've got the most famous one, the many worlds idea. It says the math is perfect, and every single possibility actually happens. It just happens in its own separate branching universe. Yeah, mind-bending is the right word.
All right, let's switch gears to another puzzle. And this one is so basic, so fundamental to our lives that we usually don't even think of it as a puzzle. I'm talking about the arrow of time. And here's the conflict, laid out plain and simple. For us, time is a one-way street. It is relentless. The past is fixed, the future is open. You can't unscramble an egg, right? But if you look at the actual laws of physics, the really deep ones, they don't care. For them, time is a two-way street. The equations work perfectly fine whether you run them forwards or backwards. There's nothing in the physics that says an egg can't unscramble itself. So, what gives? If it's not in the laws, where does time's arrow come from? Well, the leading theory is something called the past hypothesis. And the best way to think about it is with that egg. The idea is that the universe simply started in a very, very special, highly ordered state, like a perfectly unbroken egg.
The laws themselves don't care which way things go, but because we started in that one perfect state, the only way to go, statistically, is toward more mess, more disorder. So the arrow of time might not be a law of physics at all, but just a historical accident of our universe's starting conditions.
You see how these things connect? The clash between big and small, the measurement problem, the mystery of time, they're all symptoms of a deeper problem, and they all point towards one holy grail, a single unified theory, a theory of everything.
Now, for years, the big contender in this race has been string theory. It's this incredibly beautiful, almost poetic idea. It says that if you could zoom in far enough on any particle, you wouldn't see a point. You'd see a tiny, vibrating filament of energy, a string. And all the different particles and forces we see in the universe, they're just different notes played by these strings. The universe as a cosmic symphony. It's a gorgeous idea.
But not everyone's a fan of this approach. There's a strong counterargument, voiced by people like physicist David Deutsch, and he basically says, this is not how physics works. Real breakthroughs, he argues, don't come from finding a pretty piece of math and trying to shove the universe into it. They come from tackling a real, thorny physical problem head-on and figuring out the concepts needed to solve it. So what happens when our best math seems to lead to dead ends, and our biggest experiments aren't giving us the clues we need? Well, it makes you wonder, are we even asking the right questions? And this is where things get really interesting, because the search for answers is now taking a hard turn, back towards philosophy. It's asking if the solution isn't about what the universe is made of, but about the rules it plays by.
Yeah, there's this growing idea that maybe we've been looking at this all wrong. What if the answers to these quantum puzzles aren't hiding in some new particle we need to find or some extra dimension we can't see? What if the answers are in the fundamental logic of reality itself?
And that brings us to frameworks like the Bundy reciprocal system theory, or BRS-est for short. And this is a truly radical proposal. It suggests that the most fundamental thing in the universe isn't a thing at all, not a particle, not a string. It's a relationship. Specifically, the theory says reality is built on reciprocity, a kind of balanced give and take between space and time. They're two sides of the same coin. This relationship, this rule, is what everything else is made of.
So if you look at it this way, the whole measurement problem starts to look, well, less like a problem. Before measurement, a particle isn't in a bunch of places. It exists as a web of potential relationships between space and time. Then, when a measurement happens, that collapse isn't some weird magical event. It's just the universe turning potential into actual. It's the moment one of those possibilities becomes real. It's a natural process of turning many into one. And this same core logic could also explain another classic quantum mystery, complementarity. You know, how an electron sometimes acts like a spread-out wave and other times acts like a tiny little particle, but you can never catch it being both at the same time? Well, if reality is built on this reciprocal either-or relationship between space and time, that makes perfect sense. You can measure its wave nature, or you can measure its particle nature, but the fundamental logic of the system says you can't have it both ways. The choice is literally built into the fabric of the universe.
So where does all this leave us? Well, it looks like we're in a pretty incredible moment in science, where that old, thick wall between physics and philosophy is starting to crumble.
There's this amazing term for it, experimental metaphysics, and it perfectly captures what's happening. Our experiments have gotten so good, so sensitive, that we're not just measuring the properties of things anymore. We are now directly testing our deepest assumptions about the nature of reality itself. Is reality local? Is it determined? These aren't just physics questions anymore. They are, at their heart, metaphysical questions that we can now put to the test. And that brings us to the final, really provocative thought. For the last 100 years, we've tried to understand the universe by smashing things into smaller and smaller pieces, hoping to find the ultimate building block. But what if that's just not the right way to go? What if the next huge leap forward in physics isn't finding a new particle in a giant collider, but discovering a new principle, a deeper grasp of the fundamental logic that reality runs on? Maybe, to truly solve the universe, we have to solve its logic first.